Right, well, that's fascinating. Uh, let's see, how's everybody doing? Excellent. Okay, so you have homework due today, I believe, and your next homework is going to come out. The next homework includes an extra credit problem at the end where you can basically correct all the errors of your ways on your midterm and get some points back. That's completely optional, just an extra credit problem. It's up to you guys. The midterm is only worth, I think, 10% of your grade in this class anyway, so the good news is that there are plenty of ways that you can recoup things for the class. So hopefully that homework, I think, will go out probably, what, today or tomorrow maybe? At the end of lecture. Fabulous. It's a fun homework. This stuff is aligned with like what I do in my day job, so like it's like a lot of fancy, cook up a bespoke optimization algorithm for assorted problems. Kind of like, I guess, one of the problems in our homework this time around. So basically, your remaining responsibilities are pretty straightforward. You got that homework, some more quizzes, like I think just 2 more quizzes, maybe 3, not many. And final exam, which we need to write some. And other than that, you're done with this class. So we're almost there. I was looking at the schedule. There's like 5 lectures left. Okay, so any questions, comments, concerns, organizational things? No. Interesting places to go in Cambridge, restaurants. The Michelin Guide just came out. There are a bunch of local ones. Yeah. Okay, so right, well in that case, we are going to continue our discussion of optimization. Our goal today is to put something in it and finish the discussion all the way around. And then we start our final unit of this course, which is basically interpolation, differentiation, and integration. In that order, I think. I'll take that. So remember our story so far. So if we think about our optimization algorithms, we actually started with root finding because in some sense, optimization is kind of like root finding on the derivative of a function. And then after that, we went to Newton's method and all these kind of generic techniques for optimization. Then we went to the other extreme and said, well, specifically if my function is a quadratic form, then I know how to optimize it using this conjugate gradient method, which is our sort of first example of like leveraging really nice structure in our objective function to come up with an algorithm that's faster than an algorithm that only knows that my function has a gradient, right? In that case, it knows a lot, like the form of the gradient. And now, in the previous lecture, and for the rest of today, we're kind of considering problems in between, whether they fall into different patterns that are like more specialized than just minimize f of x, but more generic than minimize a quadratic form. No more lecture. Oh, there it is. Okay. So, for example, last time we focused largely on the Gauss-Newton algorithm and variations thereof, which we're designing for functions f of x are the sum of fi of x squared, which I think basically appears all over machine learning statistics and almost any other coordinate engineering. Right? Like basically, if you just have a bunch of criteria, you want to be close to 0, this is a pretty reasonable thing to do. And then we talked about a few variations of this story. So for example, the iteratively reweighted least squares problem just kind of sticks a gi of x in front of this. And basically in every step, linearizes fi and thinks of gi as a constant. And now today, like at the end of our last lecture, we talked about one particular technique which is pervasive in the computing literature. And all of these techniques, I should note, are sort of, I think the term that you see a lot is meta-algorithms. I don't know if this is a phrase you've seen before, but essentially, does it make sense, for example, for you to write a software library that implements the alternation algorithm for optimization? Probably not. This is more like a template for deriving algorithms for optimizing different objective functions, right? Or similarly here, right? Like a piece of software for iteratively related least squares is not that exciting. What's exciting is when that strategy happens to apply well to a problem that you have on hand, right? So for example, last time we wrote down the L1 version of the least squares problem and found that there's a nice sufficient algorithm for solving that case. And so that's the way to understand these techniques. These are not algorithms that you would implement the same way that you might implement Gaussian elimination. Like Gaussian elimination makes perfect sense to make a piece of code that just like factors matrix and is its own thing. I don't think it makes sense to implement most of the algorithms that we're talking about in the last lecture and today in generality. What you have to do, unfortunately for you, is a little bit of legwork mathematically to look at these different templates of algorithms, fit them to the particular objective function you have, do a little bit of mathematical work to derive an algorithm in its steps, and then implement those steps. So today we're going to see an even more in-depth example of that pattern because we're going to cover a technique called ADMM, or alternating direction method of multipliers. Out of curiosity, have you guys encountered ADMM before? I know that your TA has, yeah, a few of you guys have. But essentially, this is sort of an extension of this alternating algorithm that works extremely well and is very popular for certain classes of objectives in machine learning statistics and a lot of other fields. Actually, gosh, I probably learned about this technique maybe 15 years ago, and it really changed the direction of my own research. And I'll tell you guys about sort of how you go about deriving an ADMM algorithm. What we'll see is that the ADMM algorithm is not interesting. Like it's like somehow, you know, if you implemented the set of steps that you see in a textbook, like it's equivalent to basically implementing gradient descent or something. But that it gives you an interesting sort of plan of attack for deriving interesting algorithms for particular objectives. So another example of that we've already seen, for example, is on your homework, in homework 2, this as rigid as possible technique, right, where you ping pong back and forth between least squares and SVD problems. The thing that you might have noticed is had you had to solve jointly for all the problems in this problem all at once, right, like the vertex positions and the rotations just in one big shot, it's like not obvious how to do it. But if you freeze half the variables, if you freeze the rotations and then you get the vertex positions, it's just least squares, right? And so those kinds of patterns are very typical in this sort of alternating optimization world. So last time we mentioned a few other things, like there's beyond as rigid as possible. Incidentally, the inventor of as rigid as possible wandered into my office yesterday. Apparently she's here for a conference. So we had like a fun celebrity visit. But also like generalized principal component analysis, where you take that Frobenius norm that we saw in the Eckert-Young theorem, it's a fun final exam review, and replace it with some other norm that maybe promotes some other property for your factorization. In fact, I would say like a good recipe for NeurIPS and ICML papers when I was in grad school was to basically just put all kinds of like exotic norms in that problem on the top of the slide there, and then derive a fancy algorithm for matrix factorization. The Netflix problem, I think, was the most famous example of that, where you were trying to like, you have this giant grid of like everybody's rating of every movie on Netflix, at least in principle. Of course, in reality, you don't have access to that thing. And you kind of think of this matrix factorization as like, there's some latent feature that each person viewing Netflix has. You know, they have priority for action films, films with like, I don't know, scenes next to the water, I'm looking at the window, or whatever. Sadly, you don't have access to those, but your model is sort of that each film has the same features, each person has a list of their preferences, and the sort of the dot product between the two that predicts how much you like the film. And so what you observe are people's film ratings, which is kind of like the matrix X, and then what you want are the two factors C and Y. It's a very classic matrix factorization problem, but then people kind of typically put different priors on C and Y that make it no longer just SVD problem. And so there's all kinds of algorithms out there that basically do alternation in that particular case. Sort of in some sense, a very early success of, I don't know if you call it machine learning or statistics, at the time we called it machine learning. That really is quite pervasive today. So that's where we were last time. One additional thing that I wanted to mention is that the alternation algorithm, the way I presented it so far, ping pongs between two variables, but of course, you didn't have to just do two, right? You could have taken your variables and split them into 5 sets or 25 sets or whatever, where essentially what you're doing is you have some long list of variables in your optimization problem, and each step of your algorithm, you freeze some part of it and optimize some other part, right? And in fact, those parts can even overlap, although I think that's fairly rare. So a nice example of one extreme of that is the objective, our favorite objective in this course, which is the norm of AX minus B. Maybe with the 1/2, just for fun. Like that. And as I think, hopefully if I've convinced you guys one thing in this course, is that there's a lot of algorithms for solving this problem that have different trade-offs. Yet another one that you could derive comes from alternation. In particular, actually think back to our lectures on conjugate gradient. Remember how we derived that line search procedure? What did we do? We kind of took an objective that looked like this. In that case, it was the quadratic form. It's slightly different, but whatever. And we restricted it to a single line, right, through the current iterate in the search direction. And remember that we can do better than generic line search specifically for that objective. Does that story sound familiar? Hopefully, maybe some people. Like literally anything. Thank you guys. And why was that? Like, why can we do line search better than just like some generic gradient descent thing in that case? I mean, yes, please put me out of my misery.
That direction is kind of like a quadratic function.
In fact, it's exactly a quadratic function. Yeah, like basically this thing is a quadratic function of the variable x, which is unknown. If I take a one-dimensional slice through that thing, it's just a parabola, right? We know how to minimize parabolas. So we don't really need a line search procedure specifically for this objective. We can just do line search in closed form. Does this sound familiar at all? I hope you guys are killing me this morning. Okay. Right, so if you think about it, I mean, that line search procedure did not have to be on some fancy conjugate gradient direction. The different thing you could have done is just like search for like the 17th element of x, holding all of the other elements of x fixed, right? So in other words, like, if you think of your least squares problem as like sitting on some set of axes, I could have just like restricted to like the horizontal axis or vertical axis in any given step, and apply exactly the same formula, right? And then that becomes what we call a coordinate descent algorithm, right? And in particular, coordinate descent for this particular objective function, I think maybe I'll let you guys derive it at home because it's totally boring at this point. It's like the same calculation we've done 300 times. Is yet another way to solve these squares, where essentially what you do is you kind of maybe randomly draw one of the indices 1 through n in the length of x, and then you just throw away the current element of x and then just solve for it in terms of all the other ones. That makes sense? This algorithm, as I've described it, sounds pretty dumb. I mean, in some sense, it's worse than gradient descent, strictly, right? And even worse than conjugate gradient. Do you guys have any ideas why this might be an interesting technique? Yeah.
What if we do that all at once across different computer cores for each of the different variables?
Jonah hit the nail on the head, which is that this is a very parallelizable algorithm, right? And in particular, one thing that people do often is they say like, okay. In fact, there's a really funny machine learning paper from about 5, 10 years ago, titled Hog Wild. I don't know if you guys came across it. It's got a cute title. I think the interesting part of this research paper is actually the theoretical analysis of the algorithm. But essentially, what they do, in principle, if you want to use an algorithm like this, it's very much not parallelizable. You have to take all of x, freeze the whole thing minus one entry, replace that one entry, which involves basically looking at a bunch of columns of your matrix, and then iterate. That's quite slow. What they suggest is you have a bunch of threads on your computer, a bunch of processors that each just randomly draw an index and so apply that formula and just turn off all the locks in your memory. It's wild. So it's fun. So essentially the idea here is that there's like a bunch of little worker bees that are just like randomly like walking along this vector S and like saying, oh, I think I'll work on like element 12 of X. And just like pretend like everything else is frozen and replace that element. But like meanwhile, there's some other guy that's like walking in some other part of the problem that's trying to fix it. And what these folks show is that for a lot of structured matrices A, the probability of two of these threads kind of colliding is relatively low. And so, yeah, every once in a while you get garbage. So for example, think about like, you know, let's say that Alice's thread is working on element 15 in my vector, and like she is halfway through writing the bits of her answer back into memory while I grab it to work on element 25. So basically the number that I just got is garbage. It's actually not even like a number that does anything about my problem, right? But the likelihood of that happening is so low that actually, in general, amortized over time, you still tend to decrease the subjective function. Totally wild idea. Yeah, Jim.
Is that because the time you spend writing the new value is so much less than the time you spend doing everything else?
That's right. So for those of you who are sort of hardware oriented or computer architecture oriented, you probably know that the time it takes to write things to memory and to read things from memory is often much higher than the time to do arithmetic. And so that's a good example where like, you know, the likelihood of these two calculations colliding is pretty low. And moreover, by the way, the likelihood, like sure, I'm grabbing elements of X and maybe my calculation uses a few stale ones to make this guy. But as the optimization procedure moves forward, yeah, it's stale, but probably not that far off from my calculation. And yeah, so all of these things kind of average out over time. Really fun read. Actually, I'm unclear. I think for a little while, some companies were using this for certain optimization procedures, but I don't know in that now, like modern deep learning era where things are more GPU driven. I think this kind of technique might be a little less obvious. I'm not up to date. But anyway, all this is to mention that the extreme of these algorithms, like coordinate descent, literally updates one element at a time, and that like one of the major reasons people do this kind of thing is for parallelism. Yes.
But also help if A was poorly conditioned, because you could have, like, if it was like really stretched,
Yeah.
you could happen to get that, like, you wouldn't ping pong around until you got to the solution,
Interesting.
because you could get in one of the coordinates to it.
So the suggestion is poorly conditioned, and some method like this might do better. I hesitate to commit to that because very few things in the neural should get better if you're poorly conditioned. But I guess it is the case that, like, what is certainly true is that the gradient direction in a poorly conditioned problem is not always super useful. What's less clear is that this direction is any better. That I'm not sure, but it's an interesting idea. Yeah.
Sorry, this might be obvious. Does this converge in n steps?
Nope. Yeah, no, does this algorithm converge in like with a capital C to the exact solution? Absolutely not. I mean, think about it, like our gradient descent procedure didn't, and this thing is sort of like gradient descent, but on an even worse direction than the gradient direction. So you really don't expect this thing to converge to the solution of your problem. Yeah. But it does decrease the energy in every step, and in this case, I think you can prove, at least before you parallelize, it's pretty easy to show that like the iterates converge in the sense that they get closer and closer and closer to the optimal. Like I don't think there's a case where it like diverges. But that's different from actually reaching. Yeah. Great questions. These things are really fun to think about. Okay, so alternation is really interesting. One thing that I mentioned in our previous lecture, and I even drew you a little bit of a counterexample, at least sort of a sketch of how you can derive a counterexample, is that there's a lot of different notions of convergence here, actually, to go back to our question. And it's not so obvious that coordinate descent algorithms or alternation or whatever actually converge in the following sense. Like remember that actually if we go all the way back to like lecture 2 of this course, remember that there's like multiple notions of error, for example, there's forward and backward. So for optimization, you might think about like value of the objective function versus convergence of the like the x variable here. And we constructed examples where the x's might not actually converge even though the f values do, right? And that can be really a problem. So next, we're going to talk about a broad class of algorithms that actually are guaranteed to converge through alternation, which is kind of surprising. Sadly, in this course, because I only have one lecture allocated for this stuff, we're not going to prove convergence. But I'm going to sketch it out a little bit. That I think is worth being aware of because it's like one of these really powerful techniques that feels very abstract and I think is easy to dismiss, but then after you do the calculation a few times, you kind of pattern match and realize it's pretty straightforward. And that particular set of techniques is going to be some combination of alternation and using linear constraints on variables, and that's going to lead us to this ADMM algorithm. ADMM is a little bit weird because it's one of these techniques that looks like it applies to a very specific type of optimization function, and then what you realize is that actually no, the template, like I've very rarely encountered at least a convex problem that doesn't fit into that template. You just have to believe in yourself when you're ready to. So we'll see what that looks like. So in order to motivate ADMM, by the way, I realized this morning that I lost my notes for this class, but the good news is like if there's one lecture in this course, it's well aligned with what I do day to day for this one. So I think we can do that probably. Famous last words. Okay, so let's say that we're thinking about constraint optimization problems in general. Right, remember that we talked about like there's like no shortage of different ways to interpret the Lagrange multiplier conditions. There are so many, and we've done many of them in this course. And the one that we're going to think about for the moment is this one right here. So remember, like for now, we'll just think about equality constraint problems. And let's say that we want to minimize some function f subject to g of x equals 0. Hopefully we're sick and tired of that problem right now. That's my goal for the semester. Then one thing that we justified probably about 4 or 5 lectures ago was that you can at least abstractly think of the problem on the left as equivalent to the one on the right, which is a sort of game theoretical picture. So it's a little bit of a reminder. This is one of these things where the parentheses really matter. So like, if you take a look at this problem, this minimization over x, if you look at the left of the right parenthesis, notice that it's around a maximization over lambda, right? So the way that I evaluate a potential x is by solving another problem in lambda. Does this notation make sense? Yeah, this is very common in game theory. This class is getting nowhere close to that kind of theory, but I think at least kind of spiritually, these kinds of formulas feel right. Actually, you know, convincing yourself that this is a well-posed problem is a different matter. But in this class, that's okay. So here's the basic idea. Let's say that the player that is proposing values of x proposes a value of x for which g of x is not equal to 0, then what is the objective function of the inner problem on the right hand side? Yeah, infinity. Do you see that? Because essentially, if there's any element of g that's non-zero, I can just take lambda and just blow it up. Just put a giant coefficient in front of it, right? So from the perspective of the outer problem for x, notice that the optimal thing to do is to choose an x for which g of x is equal to 0. Does that make sense? Because otherwise, the inner problem is infinity, and that's a pretty bad objective value. Yeah? Okay. Yes, you look confused.
What happens if there is no point such that g of x equals 0?
Then, yeah, that's called infeasible, and you shouldn't be solving this problem to begin with. Yeah, good question. So, right, so let's say that we do choose an x for which g of x is equal to 0, then notice, in that case, the objective function, like the whole lambda term is zeroed out, and what I'm left with is that. So hopefully from that perspective, you can see that these two things, at least abstractly, are kind of equivalent. Obviously, like deriving the formal mathematical language to talk about the problem on the right does require some legwork. Like if nothing else, we're working with not the real numbers anymore, right? Do you see that? That's the real numbers plus infinity. So there's like a little bit of work to do. But the good news is I think in this area, intuition pretty much plays out. Like sometimes the theoretical results are a little tricky, but the high level aspects of these techniques are pretty reasonable. Now, from perspective of this formula, there's kind of an interesting thing that happens. So this is just some motivator for the Lagrange multiplier condition, right? Notice that the Lagrange multiplier condition is exactly like saying you're critical for x and lambda. But notice that lambda is trying to maximize and x is trying to minimize. So there's this like kind of disagreement. So sort of necessarily, in some sense, optimization problems with constraints are less like optimization problems and more like saddle point problems. Right? Because it's not that every variable wants to minimize, it's that like your x variable wants to minimize, and your dual variables lambda wants to maximize, and there's some balance between those two. And in fact, that really is played out. So for example, do we remember the sequential quadratic programming algorithm? Hopefully, it's still not, you guys, come on, just do all that, I don't, anything? Tashiki, I'm gonna get you to like nod sometime in this class. There we go. Okay. Right, so if you think about what happens there, remember we take a quadratic approximation of f and a linear approximation of g. So then the resulting problem becomes quadratic at every step. If you look at the matrix that you get when you write down the quadratic iteration, you'll find that it's not positive definite. Right? Which is a little surprising because even like if you're solving an optimization problem, kind of expects positive definite matrices, right? Because those correspond to bowl-shaped functions. The reason for that is that essentially the constrained part of your problem is the negative definite part of your matrix. So it's some trade-off between those two things. In fact, this formula called the sure complement is some way to bridge this gap. Now, what does that mean? That means like necessarily, like solving this problem with like gradient descent looking procedures is a little bit tricky because it's not clear whether this Lagrangian should increase or decrease in every step, right? Like there's sort of this battle between these two variables. And so there was a really kind of, in some sense stupid and in some sense brilliant observation that was made in the optimization community. This is one of those ideas that probably dates back to some Russian researcher that we'll never know, behind the Iron Curtain, written in some journal that like Americans don't know how to read, but was rediscovered in the United States maybe 10, 20 years ago, which does the following thing. It says, what if I can take this problem and like make it like at least want to satisfy the constraint a little bit, so that in other words, like these two variables are not completely at odds with one another, right? And that's sort of the very beginning of the motivation behind the ADMM technique. So in particular, here's the kind of fun transformation that I can do that actually does nothing if you think about it. Oh no, I gave it away. Let's say that I solve, let's see, minimize f of x subject to the constraint that g of x is equal to 0. So that leads us to this minimax form on the screen. And now, here's the thing that I can do. I'm going to mess with my objective function. In particular, let's say that I have some constant rho. By the way, in this lecture, I need rho to be strictly positive or nothing we do will work. That's very technical. I can have the following. I can say, I'm going to add g of x squared to my objective function. Now, let's say that so if I did this, I just made this an unconstrained problem. Notice that this would be like the barrier method we talked about before. But here's kind of a weird thing that I can do, at least theoretically, is I can do both. I can say minimize f plus rho over 2 times g, subject to g of x equals 0. Here's my question for you guys. What is the optimum of this problem relative to the optimum of our original problem? Alicia, that one really kills me. Let's think about it for a second. So when I get the optimal x, it has to be feasible. So what is g of x? 0. So what is the optimal objective for this new problem? It's just f of x, right? So what can we conclude? That I actually edited the objective of my problem. This is not the same as the problem before from perspective of Lagrange multipliers. But it is the same problem as before from perspective of like the optima that I'm looking for. Does that make sense? And so that leads to this idea, which is that actually all of the math that we did with Lagrange multipliers applies to a slightly bigger class of functions that are sort of Lagrange multiplier-like. And this is sometimes called the augmented Lagrangian, like that, which is kind of a fun idea, I think. I think it's neat. And the idea of the augmented Lagrangian, which is now lambda sub rho, is quite simple. It says, oh, it's just the Lagrangian of this thing. Usually with a minus, sorry. You might notice again that I lost my notes, so I'm doing this off the top of my head. So like likelihood of side mistakes is very high. Okay. Here's the thing. In terms of like all the theory that we've done in this class, this is a perfectly reasonable Lagrangian to work with. It doesn't affect anything at all. Because at the optimum, this term just vanishes anyway, right? But here's the thing. Let's say that I am not optimal. I'm like somewhere before that in the stages of the algorithms that we've written down so far, like sequential quadratic programming. Notice, this is now a different problem than it was before. Do you see that? Like, so for example, if I just freeze lambda and I optimize with respect to x, the presence of this term affects the point that I'm going to get. In particular, let's think intuitively for a second. Let's say that rho is really large. Then what are going to be the new optima of this problem? Like, what can I say about them kind of approximately? They're going to really roughly satisfy the constraint, right? Whereas before, if I didn't have this term here, every time I solve for x with lambda fixed, like I might fly far, far away from the constraint in some sense because of being linearized, and this feels different than optimization. Yes, sure. That's oh, sure, yeah, my bad. So, fine, you got me. There you go. Any other technical things? I'm giving him honor. He's absolutely right. I didn't say. Okay. So this leads to a very particular algorithm. This is called the augmented Lagrangian method. You might notice we're almost to ADMM, but not quite there. The augmented Lagrangian method does the following, which is kind of interesting. Now, essentially, notice as a function of the Lagrange multiplier here. So if we look at this augmented Lagrangian, hopefully I got it the same as the slides I did. But this is fun doing it from memory. Then take a look at these two updates. Remember that we're trying to maximize with respect to lambda and minimize with respect to x. Yeah? So if we take a look at this algorithm, notice that it's doing exactly that. So in every lambda step, what does this look like? If I kind of look at the Lagrangian and I look at the step in lambda with x frozen, what is this doing? Yeah, this is a gradient ascent step, right? Because it's a maximization problem lambda. Okay. And then in every other step, the kind of interesting, weird variation of this problem here is that you could have done a gradient descent problem in x. That algorithm has a name, I forget what it is. But instead, what we say is, oh, well, maybe for whatever reason, if I know lambda, I can just take an optimal step in x, minimize it. That'll clearly do better than just a gradient step. And that's what the x thing does, right? So it kind of updates lambda and then solves an unconstrained problem. And it updates lambda and then solves an unconstrained problem. Now, remember what I mentioned at the beginning of lecture, like, is this thing like a thing that you should write a piece of code for generically, not knowing lambdas, like if you're like a programming language guy? Like, probably not. This is 2 lines of code. It's like not terribly exciting. You need some black box for solving the problem for lambda. That's probably equally hard to solving your original problem. So we're not there yet, but this is sort of one of these interesting objects that people identified many years ago as some new way to handle constraints that we haven't talked about yet, and that often can work okay in practice. And so essentially, what we're going to do is expand this algorithm ever so slightly. And to be absolutely clear, our expansion of this algorithm will do worse than what's on the screen. This is, I think, a point of confusion because everybody teaches this thing first and then introduces ADMM, and ADMM is like this happy rainbow landscape. That's not entirely true in the following sense. If I happen to know how to solve this problem for X, this would be a pretty good algorithm, it turns out, pretty straight optimization. It's just the issue is that this X step typically is not particularly easy, right? There's like an operation on the right-hand side, which, like, if your algorithm itself has to call another piece of code for minimizing something, it's not very good. Do you see that? Because then you might as well just call that to do your entire problem. And so what the magic trick in ADMM is that we're going to relax this technique ever so slightly in a fashion where the minimization steps become much more tractable. In fact, we'll often be able to write formulas for them instead of just the sort of generic minimize operation that I guess you and that's what's going to make this technique useful. So it's not just this set of steps, it's the fact that the set of steps is easily implementable. So put a pin in that sentence, and we're going to see some examples, and hopefully it'll make sense to you. Yes?
Lacking the understanding for why adding this term like allows us to solve this problem more easily.
That's a good question. Yeah. I mean, you could imagine adding, writing this problem without the augmented term and seeing what happens. And it turns out often that that'll still converge. But what can happen is that if you're solving a minimax problem and you don't have this constraint term here, that essentially every time you take a lambda step and every time you take an x step, they just kind of like fly to different parts of your space because they're sort of at odds with one another. So intuitively what's going on, we have not proven convergence here, is that this x step otherwise is just dealing with a linearization of your constraint, which is sort of not enough. This is just intuition. Yes, me.
Why is like in the gradient ascent? Why is it wrong?
Why is it broke? Oh, that's a good question. Yeah, it turns out that doesn't really matter. Yeah, you're absolutely right. You could have added a different constant here. It does turn out that the converged results look particularly pretty if you use the same row. But I believe it's okay not to. In fact, one way to see that is you could have added the second augmented term to your objective. Anyway, there's a lot of ways you can work on these things. Yeah, good question. Okay. So here's what is going to happen in the alternating direction method of multipliers, or ADMM. It's basically an extension of the method on the previous slide. This is a meta algorithm, meaning that the algorithm itself is uninteresting. The interesting part is realizing that it's a pattern for how to derive an optimization technique. So we're going to introduce the algorithm, and then we're going to do a few examples so that you can see how that pattern is valuable. Okay. So the ADMM algorithm specifically applies to functionals of the form on the screen. Notice we were talking about alternation, and you kind of see what's about to happen. Like we now have two variables, x and z. By the way, there's a really good survey by Boyd and I believe Neil Parikh. That goes through like a billion examples of ADMM. It's a really nice survey that way. So if you're new to this kind of thing, I can put you there as like a place to find many examples of this thing. But essentially all of them fall into this form after doing a little bit of massaging. So basically what we're going to do is write the augmented Lagrangian of this problem. And then essentially the only difference between ADMM and the method of the augmented whatever method on the previous slide, augmented Lagrangian method on the previous slide, is that this thing is going to alternate between x and z instead of doing them all in one shot. That's the only difference. Okay? So, in particular, what is the augmented Lagrangian of this problem? Now, the fact that we have two variables x and z doesn't really matter from perspective of mathematics, right? Like, it's really like I just had one long vector of variables that happened, like I labeled the first half x and the second half z. So this is a purely notational thing. So because of that, from the optimization problem on the screen, what do we want to do? We want to minimize with respect to x and z. I'm going to try to stick to the notation in this Boyd survey, which is particularly challenging without my notes, but I've read it so many times I think we can do it. So we can have f of x plus the g is the h of z. Subject to the constraints that yeah, it's supposed to be z. Okay. what is the augmented Lagrangian from? Well, first of all, it's a function of what? It's a function of x, z, and a Lagrange multiplier. I think the Boyd survey calls it y. I kind of like lambda because this class has had lambda for everything else, so let's do that. So it's f of x plus h of z plus, so you have the Lagrangian terms as a c minus ax minus bz, plus the augmented term. I'm going to check. I did scribble a few things on my paper walking in here. I want to make sure that my science degree. Oh, back on the next slide. Sorry. I'm sorry. I'm going to flip the sign of the Lagrangian term. That doesn't turn out to matter, just to be clear, but just for consistency with the course notes. We're going to have. Okay. Does everybody agree with me that this is the augmented Lagrangian in this problem? Cool. So here's the ADMM algorithm in its full glory. It just takes place in 3 steps. It's very simple, and it cycles between these 3 things. Now remember the augmented Lagrangian method from the previous slide had 2 steps, right? It did x and then an ascent step. Here we're going to do x and then z and then an ascent step. Now first of all, do you see that this is a generalization of the algorithm on the previous slide? Like in particular, if I took h to equal 0, right, then this thing would just reduce to the augmented method from the previous slide. But essentially what this technique allows you to do is to take your variables and group them into 2 sets. And that's going to turn out to be super, super valuable. Like whoever came up with this like template was really smart. This is a really smart idea. So you might not see it yet because this feels kind of like a little obscure at the moment, but this is a pattern that fits so many different problems in machine learning, statistics, graphics, you name it. Okay? So, does everybody understand the basic steps of this algorithm? You essentially have 3 variables, 2 primal and 1 dual, like x, z, and lambda. And in each step, you freeze 2 and you optimize the third. And when you do that, the 2 primal guys are going to actually optimize completely. And the dual guy, in some sense, because it's kind of uninteresting, you're just going to take an ascent step rather than optimize it completely. That's the outline. It might not feel like this is a particularly useful method, but hopefully you see the steps. Yes, on. This thing does not maintain primal feasibility. Yeah, this thing, x and z only satisfy the constraint in the limit. Yeah, absolutely. So the intuition here is that actually by leaving the constraint set, we're going to be able to derive an algorithm that does much better than forcing yourself to move around in the constraints every time. Yeah. Okay. So essentially, I think what we're going to do, probably for the rest of the class, basically, is derive examples of using this technique in practice. By the way, there's a theoretical result, which says that so long as f and h are convex functions, this thing is guaranteed to converge for any positive row. I'm going to refer you guys to the survey that I mentioned here for a proof of that. Sadly, we don't have time in class to show that. In some sense, actually, the proof looks very similar to the proof that we wrote for convergence of gradient descent. See, it's just kind of a souped-up version of the same thing. But doing that requires some kind of careful bounds and triangle inequalities and things that I think the students in this class tend to hate. So I think the more valuable thing to do is to start being able to pattern match why this is a valuable technique and how to actually apply it in practice. And we're going to defer the proof to some reading at home. Yes, Jim?
If we already have a convex problem and we already have a lot of pretty good methods for solving that, like why is this better chosen?
So all complex problems are easy, and hence this algorithm isn't useful. That's the logic.
Well, not exactly. But just like why this as opposed to the other methods that.
So it turns out there actually are very few algorithms that apply to all complex problems generically. They tend to apply to a certain class, like linear programs, cone programs, STP. Many of those algorithms are extremely valuable, but they have some drawbacks. So in particular, what we're going to find is, for example, oftentimes A and B are sparse matrices in the problems that we care about. And the typical algorithms that you see in the very generic case for complex programming maybe aren't aware of that and can't leverage those kinds of facts. Yeah. But what we're going to see is for a lot of really nice convex objectives, and even non-convex, by the way, this algorithm you can code in like 4 lines of code, while like coding, for example, the simplex method for linear programs is like a rather involved exercise. Yeah. Good question. Yes?
this ADMM is just dividing into two vectors, or like, for example, n vector and
Oh, that is a fantastic question. So she asked, like, there's like a totally reasonable extension you might have in mind, which is, oh, well, like, why did you stop at 2? Maybe, like, do 10 different objective functions, like x, z, and w, and cycle through all of those. Here's an interesting thing. Turns out that algorithm tends to not converge. If you look at the convergence proof carefully, what you see is that it depends very strongly on having exactly 2 terms. It's a little bit surprising. Now, in reality, there are instances out there in the literature of what people call 3-block or multi-block ADMM, but they require specialized convergence proof. Generically, they don't work. Yeah. Yes. Yes, rho is a fixed constant. Now, there's fancy versions of this where they adaptively choose rho. It turns out that's unnecessary. So, from perspective of convergence theory, any positive rho just fixed, like 7. It's perfectly fine number. Now, obviously, what'll happen here, think about like what this algorithm looks like if rho is too large or too small, right? So let's say that rho is really, really, really big. Then essentially what's going to end up happening in these x and z steps is that what dominates in the augmented Lagrangian term is this giant term that just wants to satisfy the constraints. And so what's going to end up happening is that like you'll be really close to satisfying the constraint, but you won't make very much progress on the objective. On the other hand, if rho is really small, what's going to end up happening if you think about the augmented Lagrangian, they're basically zeroing out all the terms that involve the constraint, and now it's just going to keep like sticking with the minimum of the unconstrained problem, which is like a small nudge in the right direction. And so essentially the adaptive algorithms, which by the way I think are not well analyzed theoretically, like they tend to just be things people do with like vibes, is they run the algorithm for a little while and they kind of say like, oh, like my iterates are all satisfying the constraint, but my objective isn't going down, so then they get divide rho by 2, or vice versa, and then I increase it. So there's a bunch of heuristics out there that people do in practice. These are great questions. I'm glad you guys are thinking about this critically. This is one of these things that's abstract and weird. So I think what's a valuable exercise is to just do some examples of this algorithm, because again, this is an algorithm, like you would not write a piece of code for this. Strangely, there are a few attempts in at least the computer graphics community to do that. I think it's sort of a weird byproduct of this being a popular algorithm that people are like, oh, I should write software for it. I think it's kind of hard to do that in an interesting way. Maybe not impossible, but hard. The more valuable thing here is actually it gives you sort of a very fast shorthand for deriving a technique. The same way, like for example, in the first half of this class, hopefully by now, if you have a least squares objective, you're really good at deriving linear system. This is kind of a similar thing. Yeah. Okay. So. Done enough high-level discussion. Let's actually do one of these things. So we're going to start. And incidentally, there's one additional detail, or not detail, but like kind of cool thing here, which is that your objective function can actually take on the value of infinity, and that's perfectly fine for perspective of deriving these techniques. Okay. So for example, here's the problem that we're going to start with. I think actually I scribbled a few on my scrap paper right before the class. This is the one I want to do before this one. Sorry, I'm showing that so quick. Oh, yeah. So actually, before we do the one on well, sorry, I'm thinking for a second. Yeah, so one piece of art that you might want to do is to look at an optimization problem, and the first thing you might want to think about is actually how to write it in this form. And there's many ways to do that. So for example, let's say that I want to optimize min over x of a x minus b squared when it's subject to the constraint that the norm of x is less than or equal to 1. In fact, I think we've seen some version of this problem in the past, like I think on your practice picture. This problem does not feel like it falls into the pattern on the screen here. But remember that our objective functions can take on the value of infinity so long as they kind of remain convex. Remember that convexity means that like the value, if I look along the line, is always sort of upper bounded by the line between the values. So for example, let's say that I want to enforce this constraint. One way that I can do that, this is in mathematics only, this is not a thing that you code, is to add a function that's just infinity anytime the constraint is violated and 0 otherwise. Right? That kind of feels similar to our logic for Lagrange multipliers. Yeah. So for example, one thing I could do typically the notation for this is to use the letter chi. Is to define, for example, the indicator function chi of this set, which in general we're going to say is 0 if the norm of x is less than or equal to 1 and infinity otherwise. Let's think about why this is a convex function. This is a weird thing to think about as a function to begin with. But what's going on here? So let's say that I'm in the plane, and I have the unit circle sitting here. So notice that this function is infinity there, and 0 there. That's what this function looks like. And now let's say that I take any 2 points, and I draw a line segment between them. There's basically 3 cases, right? Either both ends of that line segment are in the interior of the circle, in which case this function is just 0 everywhere, so it's pretty clearly convex. There's another case where they're both on the outside, in which case it's infinity along the whole line, so it's sort of convex in some abstract sense. Or you have this case, like the line segment has one endpoint on the inside and one endpoint on the outside, but the linear interpolation between 0 and infinity is just infinity. So like clearly the function sits underneath that. This is a goofy argument, but like this is a complex function of x. Yeah. So in particular, what this allows me to do is to write this problem as a convex optimization problem as follows. Oh, sorry. I went on autopilot there. Less than or equal to. Now, I can stop here. This is already an ADMM form in some sense, where I could call this entire thing f, and then just have everything else 0. But this is not a very interesting version of this problem. Now, in particular, this is where the art of ADMM comes into play, which is as follows. What is the augmented Lagrangian of this thing? Well, first of all, like A, B, and C are all equal to 0, as is H, right? So basically, the augmented Lagrangian in this case of x, z, lambda, well, it's just A x minus b plus the norm, right? Because there is no augmented term in this case. Now, here's the thing: does ADMM converge for this augmented Lagrangian? Absolutely, right? Because what like let's look at the iterations of this technique. The first step is minimize with respect to x, the augmented Lagrangian. In this case, that amounts to solving the problem. And then the other step, do nothing. Yep, conversion one step. Is this a useful algorithm? No, right? Like this is just a more complicated way of writing the thing that you started with, right? Is everybody with me so far? We see that this algorithm on the screen as written is not useful. What's useful is of the pattern. So basically, the art of these ADMM techniques comes in rewriting your problem in a way that is sort of amenable to ADMM style algorithms, right? So in particular, for this problem, one thing that we could do is rewrite. We could say the following. Let's say instead, I'm going to minimize ax minus b plus the indicator that z as the norm less than or equal to 1, subject to the constraint x minus z equals 0. Do we all agree this is the same problem as what we started with? Right? All I did is I took my variable and I copied it twice. Yes?
I don't understand the z factors in here. Like, I don't understand the rewriting.
Sure. So essentially, right. So remember, this is the problem we're trying to solve. This guy's just fancy notation for the same problem. But applying ADMM to this form isn't particularly useful.
I understand it now. You just said x equals z, and then
Yeah, that's right. So like all I did was I made 2 copies of x. And now here's the thing that like for now it's gonna feel like, oh, Justin just like happened to pull this out of my hat and this algorithm work. But we're gonna see that there's a pattern to it. What is the augmented? So this is the bad augmented Lagrangian. What's the augmented Lagrangian of this guy? Well, it's gonna equal ax minus b plus the indicator that the norm of z is less than or equal to 1 plus, now we need an augmented term x minus z plus rho over 2 x minus z squared. Do we see that like even though these are the same problems, they have different Lagrangians? Like because when we reshape our problems, the Lagrangian can change. Now let's eyeball this, and then even though it's maybe not what was in my slides, since I'm doing this live anyway, we'll just work out that ADMM algorithm for this and get wrong and frustrated halfway through. Sound good? Okay. So this thing feels more complicated than the previous augmented learning. It's certainly longer. There's more symbols here. But remember, what does this algorithm do? It freezes x and it optimizes for z, and then it freezes z and optimizes for x. And the third thing, but this is the formula, so like we're not too worried about it. Okay? Now, what does that mean? That means that the art of designing these algorithms is to write it in some form where when I look at its augmented Lagrangian, if I freeze off the variables, it's easy to solve. Do you see that? So in particular, let's look at this problem and suppose that I froze z and I froze lambda, and I just optimized for x. So for example, does this indicator term do anything for that problem? No, we're gonna only focus on x. So I could remove this term. Now, hopefully by now in this class, you can begin to eyeball what's gonna happen. How am I gonna solve for x? What was that? Yeah, this is a linear system of equations. See that? This is a least squares problem. Wait, when I freeze z, all the nonlinearities went away in my problem. And what I'm left with is just least squares for z. Yeah, it's got multiple terms. I'm going to be careful about that. We'll do it carefully in a second. But the problem itself is actually not so hard anymore. Does that make sense? Isn't that cool? Moreover, what's going to happen when we freeze z, this one may be a little bit less obvious. The terms involving the matrix, like A, notice that there's only an x here, there's no z, so this term goes away. And everything else is element by element of z. So it turns out this is going to look like a distance function. That's what we're going to see in a second. Okay? So let's actually work out the algorithm. That's not the one in the slides, but yeah, what the heck. Okay. So, here's what you have to do in ADMM. You don't code the thing in the box, you derive the three things in the box, and then you code that. Okay? So, by the way, it doesn't really matter what order you do x, z, and lambda. That's irrelevant here. Convergence works forever. So, which one do we want to do first? Let's do x. Okay? So, x. So, as a function of x, notice that what is this problem? It's min over x, the norm, ax minus b. I stupidly didn't put a 1/2 in front of it, and I'm going to suffer a lot of 2's, but that's okay. The chi term doesn't matter. I have plus lambda transpose x. Notice that I don't need the lambda transpose z because I'm just focused on x. Yeah. Plus rho over 2 x minus z squared. Cool. Hopefully now this problem starts to look familiar. This is like problem 1A on your exam, but at least a third of you got, right? Which makes me a little sad. Okay. So let's take the derivative of this thing with respect to x. What am I going to get? I will get 2a transpose a x minus 2a transpose b plus lambda plus rho over 2 x minus z. Did I do that right? Yes, to me, I didn't do it right, did I? Oh, you're right. That's yeah. Thank you. That's close. Okay. All right. So in particular, remember our goal in this step of the algorithm is to solve for x. The other variables are frozen. So in particular, notice that this is 2a transpose a x plus rho from the identity, like that, minus 2a transpose b minus rho z, like that. So in particular, then we find that x is equal to 2a transpose a plus rho I inverse 2a transpose b plus rho z. Cool? At this point, this step of this algorithm should be pretty rote for you guys. Yep? Yes, what happened to the lambda? I probably forgot it. Oh, yeah, there's a lambda there. Oh, yeah. My turn. Yeah. Incidentally, notice that this matrix does not change from one iteration to the next in ADMM. So what else can I do to make my code even faster here?
Hash the factors.
Yeah, I can refactor it. And in fact, notice by the form of this matrix, it is guaranteed to be positive definite, right? So I can apply Cholesky factorization. Okay, so that's step one. And now you start to see why this ADMM algorithm is so valuable, that like our original problem, it's not obvious how to make progress. On this problem, because I've separated it cleverly, now when I optimize for X, I don't need to take a gradient step. I can just write a formula for what the optimum is this thing. Cool. All right, so next, let's do Z. Okay. So now we need to minimize our that is not our Lagrangian with respect to Z here. So we can do the kind of same exercise. We can just for like visual quality, we can strip out all the terms involving X and lambda and just leave Z. So in particular, we have a minimization over Z. Does the AX minus B term matter? No, not for the problem in Z, right? So we're going to actually take that chi term and put it back as a constraint, like that, right? Because minimizing this is always the same thing, that constraint back. And now we have basically two terms. We've got a minus lambda transpose Z plus rho over 2 X minus Z. Like that. Everybody agree with me? You shouldn't. I've already made like 5 mistakes. Okay. Now, this is actually a very common pattern in ADMM. Like one of the two iterations ends up being a linear solve. The other ends up being something you have to be a little bit clever about. But in particular, I think the really beautiful thing to notice about this splitting is that the matrix A is not here. Right? There's actually no coupling between the elements of Z. You see that? So here's a thing you can do. This thing is quadratic at Z plus a linear term. So we're going to complete the square. Right? So in particular, we have minus lambda dot Z plus rho over 2. We got X squared minus 2x dot Z plus Z squared. Everybody agree with me so far? Cool. Now what we need to do is basically just incorporate that lambda term in the inside of this thing. Okay, so what I'm going to get, this is rho over 2, and we have 2 over rho with a minus lambda dot Z plus the null of X minus 3x dot Z plus Z squared. Okay, so all I did was take this guy and move it to the inside of the parentheses. All right. And now here's the kind of clever trick. Remember that our optimization problem here is with respect to Z, right? So like for all intents and purposes, this X term is actually just a constant. I could ignore it. Do you see that? Moreover, I can actually combine these two terms. So I've got X dot Z and I've got 2 over rho lambda dot Z. So in fact, I claim this is some constant plus rho over 2 times the norm of Z minus lambda over rho plus X squared. So, you guys all agree with me? I'm doing this off the top of my head, so completing the square off the top of my head is a dangerous thing. Yes, on.
Pretending that lambda is constant with respect to this.
That's right. So in this step of the algorithm, we only care about Z. Everything else is a constant.
But lambda is defined in terms of X, Z as well.
Sorry, you mean little lambda here?
Yeah.
Yeah, so little lambda is just defined for the other guys. The other guys also written in terms of lambda, right? They're all glued together. But the idea in this algorithm is at every step we freeze 2 and we optimize 1. So here we are freezing lambda and X and we're optimizing for Z. So in particular, if you kind of expand the square, notice what you're going to get. You have a Z squared term here, right? You've got a 2Z dot lambda here. You got a 2Z dot X there, right? And then everything else kind of doesn't matter. Like you have this lambda over rho, the base of the norm of the second term squared. But with respect to Z, that's just a constant. So like from perspective of optimization, that actually is totally irrelevant. Do you see that? Does that make sense? So in other words, trying to see if I can complete the thought here. I claim that we can rewrite our z step in a different way, which is the following. It is the min over z. We can get rid of all the constant terms, and the scaling for that matter, of z minus rho over 2. Oh, wait, 1 minute, sorry. Z minus lambda over rho plus x squared, subject to the constraint that z has normal center equal to 1. Cool? Yes?
Why did we have to make the simplification? If we were to just go for the function as was written,
You could have, yeah, that's perfectly fine. Like, you could have written Lagrange multiplier condition for the first thing and like work your way through the KKT. The reality is that's unnecessary here. There's a much simpler way to derive it. Oh. So what is this function? Remember, this is some constant. You can give this thing a name, we can call it Q, right? Or maybe Z naught, right? This is the distance between Z naught. So think about what this is saying. This is saying that I've got some point Z naught, I've got the unit circle, and I'm trying to find the closest point to Z naught in the interior of the unit circle. That's all this optimization problem is saying. So from here, it's actually quite easy to write the Z step of our algorithm. You see that it's actually sort of takes place in 2 steps. So there's 2a, which is maybe to compute Z naught as lambda over rho plus x, right? And then step 2b is Z gets one of 2 things. It either gets Z naught if the norm Z naught 2 is less if the 2 norm of this vector is less than or equal to 1, and Z naught divided by its norm, which is the projection onto the unit circle, otherwise. Do you see how we derive this formula here? Okay, so let's stand back. By the way, and then what is step 3 of our algorithm? This one's closed form. No, if we peek at our augmented Lagrangian here. Remember, what does it do? It just does. You just kind of take the linear part, multiply by rho, and add it to that. Right? That's the pattern. So, what did we start with and what did we get? We started with an optimization problem. Somewhere. Here. Right? As you know, I'll get you a thing. So, our goal is to find x. From perspective of this problem, it's not entirely obvious how to solve it. It turns out for this particular problem, there's a lot of ways to do it. We rewrote it in a form that was amenable to ADMM. But we didn't stop there. We derive the x, z, and lambda steps as formulas. Like it's not like you just call a piece of code and give it a pointer to this thing. Like we have to actually work out those formulas. But now take a look. This thing is implementable in 3 lines of code. Do you see that? Essentially, one of the lines of code, which is on the top board here, just replaces x with the solution of the linear system here. One of the lines of code is just a formula. One of the lines of code is another formula. If you type these 3 lines of code into Python, what you'll see is that x and z converge to one another, and they converge to the solution of this problem. Cool? So now you see the power of this algorithm is that by very cleverly choosing that splitting, now the individual x and z steps are actually not so hard. Yes, Sushi.
I understand this, but like my question is, this is really stupid question that
No such thing.
like chi is infinity. Can we like minimize the x in terms of x?
Chi is infinity. Can you minimize the x problem? Yeah, that's a good question. So if you think about it, in every step, chi is actually equal to 0, so long as you choose a feasible point to start at. Yeah. Otherwise, you're right. This algorithm. So, yes.
How did we come up with the lambda update stuff?
Yeah. So this is just a gradient ascent step in your augmented Lagrangian. Right. So if you take a look, so this is just a formula. So in general, the ascent step is just rho times the linear constraint, whatever it is. So in this particular case, it's just x equals z. The way to understand this step is that if you take the gradient of our augmented Lagrangian, you'll see that's exactly that term there. And the reason for that is that, like, as a function of lambda, this thing is linear. So, like, you can't solve the maximization problem with lambda. It'll just be infinity. But what you can do is take a single step. Yeah, good question. So let's see, we got a couple minutes left. Yeah, so maybe we'll derive really quickly one more ADMM algorithm just so that we kind of see the pattern one more time. This is actually kind of similar. Oh, do we want to? This one's a little bit close to the previous guy. So the one that I intended to do, but then I got carried away with the example that I wrote on the board, is non-negatively squared. So this is probably a better example for ADMM because the reality is that this problem, you actually can kind of eyeball a solution to this particular problem. But what the heck? Actually, we can do this one really quick. This was actually kind of, in fact, I'm tempted. I think you could even derive a non-negatively squared algorithm by just strategically erasing lines on the board here. What the heck? We got time. So let's say that I wanted to solve non-negatively squared. By the way, notice that none of the algorithms we talked about in this class really directly apply to the problem on the screen, except they're really generic optimization techniques. Non-negatively squared is a really critical problem in a lot of areas of statistics, and just that darn inequality constraint is already enough to make this a hard problem. In fact, by the way, as a special case, so this problem is all linear programming, so you kind of expect this to be hard. Okay, so let's say that I wanted to solve non-negatively squared, so actually we already have kind of a nice way to do that. I'm going to do a thing students hate, which is go through our old proof and just make a few edits and see that we get an algorithm. All right? Can we do this together? I think we can do it. So, by the way, does everybody have in their notes the previous one that we did? Okay. So now, let's say that I want to solve this problem. I want x to be strictly positive. Right? This is a problem that typically people will probably like active set method to or something. It's actually not so obvious how to solve. Okay, so what could we do? Well, we can actually, in this particular case, go through exactly the same pattern we had before, but now every time we have the norm constraint on x, we can replace it with non-negativity. So like for instance here, and then maybe for fun we'll do a third example that doesn't fall into this category. We can just kind of substitute it like that. Kind of lots of guys so far. This is just a small edit of our previous thing. This is what I should have done to begin with, but that's okay. All right, so let's take a look. If we go to the three steps of our algorithm, first of all, does the x step change? No. Cool. Now, let's take a look at the z step. If you take a look at the z step, the only thing that changed was the constraint. So now we have the following, z greater than or equal to 0. Yeah. So notice that like all the math that we wrote down is actually still fine. And what we end up with is this problem, z greater than or equal to 0, like that. So the only thing that changes is just this one line of code, where now, what are we trying to do? We have the distance between z and z naught, that z is positive, element-wise. So if you think about it, what that means is that z should be the max of 0 and z naught, element-wise. That's it. Now we have an algorithm for non-negatively squares. Cool? So the kind of neat thing here is that, like, this is a problem that is hard to solve. Like, there are a lot of algorithms out there. Like, this is a quadratic problem with a bunch of linear constraints, one per element of x. But there's sort of a few nice advantages of this particular technique. I think the main one is just that it's 3 lines of code and you solve a really non-trivial problem. And moreover, you can prefactor your matrix, so those 3 lines of code run relatively fast. Yes, I mean.
So you can also solve any constraint that's like a complex equal set. You just project it.
That's absolutely right. And in fact, there's a reason for that, which is that ADMM is something called a proximal algorithm. Proximal here, meaning closest point. And in fact, one thing you might notice is that a thing that shows up often in these algorithms, it's great when I have a plan to the audience, is exactly that. It's somehow like a projection operator. And it turns out there's an entire class of optimization techniques that are built on exactly this thing, where you take a function f, you add a distance term to it, and you minimize. And now, this is one of these things where, like, generically speaking, this is equally hard to minimizing f, right? Like for just some generic f, accessing its proximal operator is a hard thing to do. But there's a bunch of f's for which the proximal operator is pretty easy. For example, here we use the proximal operator of the non-negative worth-it, or before that the unit ball, and in both of those cases it was just a thing we could work out by hand. Now, here's a fun exercise that we're not going to do in lecture. You can actually take the 3 steps of ADMM and write them all as proximal operators of different functions, like h and f in particular. So really, what ADMM is doing is applying prox back and forth between 2 different functions. And the idea is that a very common pattern in optimization is that the sum of 2 functions, prox operator is often quite difficult, but the individual ones is not so hard. Like in our case, it was the least squares and a projection. And that when you have that pattern, that's really when ADMM works. Now, to give a third example of a problem you might apply ADMM to, and then we'll spend our last couple minutes talking about one more possible method if we have time. Here's a very typical problem with statistics. You might notice a lot of these things start the same way, which is minimize the L1 norm of AX minus B. Here's a fun puzzle, is how might you apply ADMM to this particular problem? Now, there's not a single right answer, there's actually many. In this particular case, here's the splitting that I would suggest, and maybe I'll let you guys work out the iterates at home. Really, by the way, when I say that, you should do it. Like, my evidence from your midterm is that you guys aren't doing that when I suggest it, but like, try this calculation. If you're stuck, come to Osner, like, we'll do it together. Let's take a look. So, let's say that I have x and z. One thing that I could do, kind of borrowing from over here, is minimize the L1 norm of z subject to the constraint ax minus z minus b is equal to 0. Right? Or it will be on the right hand side, whatever. Now, we're not going to write the whole possible algorithm for this, but let's kind of eyeball it and see why this is a reasonable thing. Okay? So, first of all, you all agree with me that this is equivalent to the original problem? Now, here's the kind of pattern you might notice. There's no a in front of z, right? Z is kind of like element-wise decoupled now. And in fact, when we write the Lagrangian for this thing, we get the L1 norm of z, which by the way is not differentiable, so which is another reason why these algorithms are kind of nice. Plus, I've got a rho over 2 ax minus z minus b squared plus lambda dot product ax minus z minus b. Now, if I freeze z and I optimize for x, notice that the same pattern applies from before. This is like a least squared problem, right? Or like a quadratic function. So we're going to end up with a linear solve. Does everybody agree? Okay. The lambda step is just a formula, so we're not terribly worried about that. The z step, well, if you think about what's going to happen, it's kind of an interesting thing. The objective function is going to take kind of a funny form. It's like the L1 norm of z. Now, if you take a look at the quadratic term, remember that anything involving x and b is just a constant, right? So it's kind of like rho over 2 norm of z minus some z naught, whatever it is, squared. Yeah. Notice that like I can actually do the same, complete the square to incorporate the linear term, right? So from this perspective, this does not fall into the category that we did before. It's not a projection anymore. But notice that actually, what is the subjective function? Well, it's really the sum over I of the absolute value of zi plus rho over 2 zi minus z naught I squared. Yeah. Do the elements of z have anything to do with each other? Yeah. So the beautiful thing that happens in this particular case is that to solve this guy really is to solve n different problems, one for each element of z, one by one. Yeah. And moreover, by the way, it's actually pretty easy to work out a closed form formula for this thing once you try that out. It's a little bit annoying. You have to do 2 cases, right? Like either the absolute value is positive or negative, both of those are quadratic, and then you just have to glue them together. Okay. So anyway, all of these algorithms are built on the proximal operator. The proximal operator is this weird thing defined on the screen here. And in general, what I want to convince you for is that as we move toward solving differential equations, this object is actually going to look very familiar to us in a few lectures. In particular, we're eventually going to solve ordinary differential equations with the form x prime equals f of x. We're going to think of gradient descent as kind of like a forward Euler discretization of this problem. And the Proximal operator is kind of like a backward Euler discretization. For those of you who come from mechanical engineering, that might make sense to you. And if it doesn't, we'll return to that sentence in a few lectures. But essentially, my point is that this proximal operator, let's see what it does, at least kind of locally. This I did write in my notes before class. Which is as follows. Somewhere. Ah, okay. Oh, right, by the way. Oh, no. I got excited. All right, actually, maybe we'll defer on proximal things. What we're going to do in our next lecture is help you understand why essentially this thing kind of looks like gradient descent on F when C is large enough. But I'm going to defer that to next time. My apologies that this is a little bit discombobulated because it's off the top of my head. And then we'll derive a really fun algorithm for, like, let's say that I want to solve AX equals B, but A is really poorly conditioned. Then what we're going to show is we can use proximal point method to solve A plus a big multiple of the identity equals to B, and do that a few times to converge on the solution of our problem, which improves the efficiency quite a bit. So that's what we'll do next time. Yeah, I'm sorry to forget. I wanted to cover one additional application of ADMM. Is that okay? Really quickly, we can do it in 2 minutes. And the reason is that we talked about parallel algorithms for optimization, and I wanted to mention one really fun parallel algorithm that's actually a byproduct of ADMM. And that's the following. Let's say that I want to solve, by the way, our Gauss-Newton algorithm kind of falls into this category. Let's say that I want to solve the sum of a bunch of FIs of the same variable x. Okay, we're going to actually derive a really generic algorithm for this particular problem, unlike the previous 2 examples, which were really formulas. This is just another kind of attack. Here's the thing, in a lot of applications, fi of x probably doesn't involve all the elements of x. So for example, think about in differential equations or physics, like f equals ma, maybe x is like really discretizing the unknown of some problem along a big line, and then like maybe fi of x just involves like x3 and its 2 neighbors or something like that. This is a very typical situation. The one thing you might want to ask is, can I do some version of optimizing this big sum? But the problem is that it has a bunch of terms. So like maybe this one couples those together, there's another one that couples these together. So there's global information moving around in that sum, but any individual term only couples a few elements together, right? Or as another set of problems, think about like a social network. And it has some prior, like, I'm trying to infer some information like, oh, if I know, Alice is over here and Alice makes lots of money because she's a graduate student and she's got this social network and there's like some other people over here, they make less money, and I'm trying to like guess, the money that happens between. That's very typical to maybe have an objective term for every edge in my network, right? So that would be like every FI, which maybe says that like, Alice, her income is similar to Mark and me because they sit next to each other in class. I think that's actually true with 100% precision in this case. And so you can imagine how the individual FIs each only maybe involve 2 of my variables, even though there's really 1 variable per term in this problem, right? And so there's a whole class of algorithms out there that are called consensus that say, I want to optimize things with this form. In the biggest case, maybe this is the graph of the entire internet. And I've got like processors that are kind of crawling around that graph, and they want to just make things a little better than they were before, right? But I need to convince myself that the whole thing is going to converge. So in like -2 minutes, here's how we can derive an ADMM technique for this, which is kind of cool. This is as follows. Let's say I minimize over x and z the following. What I'm going to do is I'm going to put a bunch of xi's like that. Remember, the fact that x isn't like a bunch of vectors is just notational. And I'm going to write sum of fi of xi subject to the constraint xi minus z is equal to 0. Do we all agree that this is the same problem? You see the kind of pattern in these ADMM things, like you sort of take a problem, you decompose it in a nice way, and then you work out the iterations. So in just a minute or 2, what's our augment of the Lagrangian of this thing? It's going to be f of xi plus the sum of, by the way, this is the world's most complicated 0, rho over 2 xi minus z squared plus And now notice that you need a different Lagrange multiplier for each term in the sum, like that. Dot product xi minus z. Cool? Hopefully we all agree. So here's the thing. We can actually do ADMM applied to this thing. Okay, so we have an x block and a z block, like that. And let's see what's going to happen. So for the individual x blocks, remember that z is now frozen. What does our x iteration look like? Well, this effective function is just a giant sum over indices I with no coupling between them except by virtue of that z, right? So if that z is just a constant, then essentially what I'm going to do is that I really have min over xi of f I xi plus rho over 2 xi minus z squared plus and I dot product xi. But this is a problem that only involves xi and none of the other variables, right? So if f is kind of local in nature, then I can solve this problem locally and totally ignore everything else in my problem. Do you see that? It's not quite the same problem as the original one. I've had to add a little bit of a least squares term that kind of prevents me from moving too far from the consensus. But that's the only difference. Isn't that cool? Now let's take a look at the z problem. I promise we're almost done. Well, what is the z term? Well, you can actually kind of eyeball it. It's basically just the average of the x's plus some correction in volume and that's it. Cool? So in any event, the details of this algorithm were worked out in the book. Obviously, we're way over time, so we'll stop for the day. But this is just yet another example of this algorithm pattern being useful in everyday life. In this case, it's useful not only for coming up with like kind of efficient algorithm, but for also coming up with parallelization techniques, where maybe the f's actually only involve a few of the elements of x, whereas the original problem couples them all together, and now we can parallelize over all the x steps and then do a relatively simple formula to gather them all back into the z. That makes sense? Cool. So when we start next time, we will conclude our discussion with a bit of mention of this proximal operator, and then we will finally enter the last chapter of this course, which involves integrals and derivatives. The good news is even if you totally lost the last two lectures,